Good evening. I am J.Arockia, St.Joseph College of Arts and Science, Cuddalore, Assistant Professor Mathematics. And today we are going to see some important theorems in algebra. Before entering to the lemma, we just try to recall the definitions of internal direct products, namely external direct product and internal direct product. We know that internal direct product of G for the given two subgroups A and B, then it can be written as G equal to A bar into B bar. Also, the external products of G for the given subgroups A and B, we have G equal to A cross B. Using that, we now see a lemma. First we say the statement. Suppose that G is in the internal direct product of N1, N2 and so on Nn. Then for I not equal to J, Ni intersection Nj equal to E, and also we have to prove that if A belongs to Ni and B belongs to Nj, then AB equal to BA. Here in the statement it is understood that for the given group G, we have n normal subgroups that are N1, N2 and so on Nn. And for the second part we have to prove that it satisfies the commutative property. First we see the first part. So for the proof, given G equal to N1, N2 and so on Nn, let X belongs to Ni intersection Nj for I not equal to J, and also J greater than I say. If X belongs to Ni and X belongs to Nj, then X belongs to Ni implies X can be written as X is equal to E1, E2 and so on Ei minus 1, X Ei plus 1 and so on Ej and En. Let it be equation 1. In the equation, the X is placed in the ith place. Similarly, if X belongs to Nj, then X can be written as X is equal to E1, E2 and so on Ej minus 1, X Ej plus 1 and En. Let it be equation 2. Similarly, here X is placed in the jth place. In both the equations, all Ei's and Ej are equal to E. But we know that every element of G and so in particular X has a unique representation in the form. Yes, whether it is an internal direct product or external direct product, the representation of any element in G is unique. Therefore, if X can be written as X is equal to M1, M2 and so on Mn, where M1 belongs to N1, M2 belongs to N2 and so on Mn belongs to Mn. Hence, equation 1 and 2 must be identical. That is, ith entry in 1 equal to jth entry in 2, or jth entry in 1 equal to ith entry in 2. This implies Ej equal to X or X is equal to Ei. And also this implies X is equal to E. Thus, Ni intersection Nj equal to identity for I not equal to J. And for the second part, we have to prove the commutative property, that is AB equal to BA. Now, let A belongs to Ni and B belongs to Nj. We take so, where I not equal to J. As B belongs to Nj and Nj is a normal subgroup of G, then B can be written as some GB G inverse belongs to Nj for every G belongs to G, which is also can be written as AB A inverse belongs to Nj. Again we consider an element in Nj, that is B inverse, because as for our consideration we have taken B in Nj and Nj is a normal subgroup, then its inverse also will exist. Therefore I can write it as AB A inverse into B inverse also belongs to Nj, which implies AB A inverse B inverse belongs to Nj. Let be equation 1. Again, as A belongs to Ni, we can say that A inverse also belongs to Ni. Then the element A inverse in Ni can be written as some G inverse G A inverse G inverse belongs to Ni, which also can be written as B A inverse B inverse belongs to Ni, since B belongs to Nj, which is a subset of G. And I take an element in Ni, that is A, and I multiply it. Therefore B A inverse B inverse belongs to Ni, which is equal to AB A inverse B inverse belongs to Ni. And let it be equation 2. Now looking at the equation 1 and 2, in the left hand side both are equal. Therefore AB A inverse B inverse belongs to Ni intersection Nj. But we know that Ni intersection Nj equal to E. Therefore AB A inverse B inverse is equal to E, which is equal to AB equal to BA. Hence we have proved it. Also we see a theorem. The statement is, let G be a group and assume that G be the internal direct product of N1 to Nn, and let T equal to N1 cross N2 cross and so on cross Nn. Then we have to prove that G and T are isomorphic. Here the statement directly says that we have to prove the isomorphism between the internal direct product and the external direct product of n subgroups, namely normal subgroups. So G, the group, is internally written as N1 into N2 and so on into Nn, and it is externally written as T equal to N1 cross N2 cross and so on cross Nn. Now we move on to the proof. So since we have to prove the isomorphism, we first define the function, that is psi is from T to G. We know that T is external and G is internal, which is defined by psi of A1, A2, and so on, A3 and so on, An, which is equal to A1 dot, A2 dot, A3 dot and so on, An. For every A1 belongs to N1, A2 belongs to N2 and so on, An belongs to Nn. So the function is defined. Now we see onto, that is psi is onto. Clearly psi is onto for every A1 belongs to N1, A2 belongs to N2, A3 belongs to N3 and so on, An belongs to Nn. We define it by psi of A1, A2, and so on, A3, and so on, An is equal to A1 dot, A2 dot, A3 dot and so on, An. since G is internal direct product of N1 to Nn. So therefore it is onto. Now we see whether this psi is 1 to 1. We know to prove 1 to 1 we take two elements from the domain, and namely A1, A2, and so on An, and B1, B2, and so on Bn belongs to T, such that psi of A1, A2, and so on, An is equal to psi of B1, B2, and so on, Bn. By the definition, it is equal to A1 into A2 into A3 into and so on An, B1 into B2 into B3 and so on into Bn. We know that since these two are equal and the representation is unique for the subgroups, normal subgroups N1, N2 and so on Nn, it is clear that A1 must be equal to B1, A2 must be equal to B2 and so on An equal to Bn, which implies A1, A2, and so on An is equal to B1, B2, and so on, Bn. Therefore, psi is 1 to 1. And now we see whether this psi is homomorphism. Again, to prove homomorphism, we take two elements from the domain. We name it as x and y, such that x is equal to A1, A2, and so on, An, and y is equal to B1, B2, and so on, Bn. Then we have to prove that psi of xy equal to psi of x into psi of y. Then psi of xy is equal to psi of A1, A2, and so on, An into B1, B2, and so on, Bn. As it is in the product, it can be written as psi of A1, B1, A2, B2, and so on, An, Bn. And now by the definition of psi, it is equal to A1, B1 into A2, B2 into and so on into An, Bn. If I is not equal to j, then Ai Bj must be equal to Bji, which can be also written as A1 into A2 into and so on A3 into An, and B1 into B2 into B3 into and so on Bn. And again by the definition of psi, it is equal to psi of A1, A2, A3, and so on An into psi of B1, B2, B3, and so on Bn, which is equal to psi of x into psi of y. Therefore, psi of xy is equal to psi of x into psi of y. Thus, we have proved psi is 1 to 1, onto and homomorphism, and therefore G and T are isomorphic. Thank you.